In this video, we'll measure the rise time of a fast-rising signal and use these values to estimate the bandwidth of the ADALM2000 and also a Siglent oscilloscope. The rise time of a signal is defined as the time it takes to go from 10% of its low value to 90% of its high value. A scope's bandwidth can be measured by feeding it a sine wave at a low frequency and noting its amplitude, and then increase the frequency until the amplitude is reduced by 3 decibels. As we'll see, this bandwidth also determines a scope's ability to see or measure a fast rise time. A Raspberry Pi Zero should be able to produce a signal with a fast rise time, so we'll measure this using the M2K and a Siglent oscilloscope, and then we'll see if the rise times relate to the bandwidth in the way we expect. Theory says that the shortest rise time that a scope can measure is equal to 0.35 divided by the bandwidth of the scope, where the rise time is measured in seconds and the bandwidth in hertz. Our Siglent oscilloscope has a rated bandwidth of 100 MHz. That suggests that its shortest rise time that it can measure should be about 3.5 nanoseconds. The M2K's rated bandwidth is 25 MHz, and that suggests that the shortest rise time that it can measure should be about 14 nanoseconds. Let's use Scopey to measure the rise time of the Raspberry Pi. I have signal 1 plus connected to pin 18 of the Raspberry Pi, and then 1 minus and a ground from the M2K are connected to ground pins on the Raspberry Pi. The Raspberry Pi has some useful features for this test. I have software that sets up a hardware generation of a square wave at 2 megahertz, and also the software can control the drive strength of the outputs on the Raspberry Pi, and the drive strengths can range from 2 milliamps to 16. So one of the things we can do is to see if changing the drive strengths change the rise time, which theory dictates it will. The higher drive strength can produce a faster rise time. We have Scopey running with the Raspberry Pi set to 2 milliamps drive strength, which is its smallest. So what do we see? First of all, I'll call your attention to our sample rate here. It's at 100 megasamples per second, and because the channel is set to 100 nanoseconds per division, we're actually only getting 10 samples per division. So 16 divisions, 10 samples each, to a total of 160 samples. And so the sample rate limitations of the M2K mean that what we're trying to measure here, just this rise time, we're near the limits just imposed by the sample rate itself. So that's interesting. So what's the best way to measure? So let's turn on the measure menu, and we can see that it measures rise time over here. But this is, I think, more of an instantaneous measure, and it may be better to, let's get the measure menu here, to use this number down here, which is a statistic that is averaged over time and thus might be a little bit more accurate. And you can reset the statistic by clicking on reset here, and then it starts averaging again. And so you can see that it's showing about 20 nanosecond rise time. And that's good. One thing we can do is zoom in like this. Oops, I did it too much. Zoom in like that, and then use the cursors to try to see if this looks even plausible. So I just have to eyeball the 90% and the 10% point here. And then the cursors are saying, let's see, they are saying that the delta t is about 18 nanoseconds. So that's somewhat consistent. But we can see that the curve is jumping all over the place. So that's why the averaging method is probably good. But at least the cursors and what it's showing in the average look consistent, so that gives us some confidence. So let's turn off the cursors and maybe get the measurement menu back. So I'll do another reset. It's nice to see if it ends up in the same place after multiple trials. So once again, around 20 nanoseconds. So now let's just change the Raspberry Pi to go from its minimum drive strength of 2 milliamps to its maximum of 16 milliamps. And I probably should zoom out. And so you can see, let me actually go back to 2 so you can see the transition. So here's the waveform with 2 milliamp drive, and here's the waveform with 16. And so you can see that we're getting a little overshooting now and a little bit of resonance. And that's consistent with the higher drive strength giving us a faster rise time. So let's reset this average and see what we get. And so now it's showing a rise time of around 11, but kind of growing. And so now it's up to 15, down to 14. So it looks like it's stabilizing around 14 nanoseconds, which is consistent with what theory dictated from the 100 megahertz, the 25 megahertz bandwidth. So let's reset again and see what we see. And this looks like it's being pretty consistent. And then once again, we could try zooming in and using the cursors to try to double check. And this is harder, I think. Maybe that's probably not right. Something like that. And so now it's showing 8 nanoseconds, but I think it's very difficult to use the cursors here. At least what I'm seeing isn't inconsistent. Notice that the average has declined to 11.8. That's curious. If I reset that, will that remain, perhaps? If I zoom back out and reset. So it looks to me like that the measurement is affected by the zooming in Scopey. So does it get more accurate if I zoom in? Who knows? I think the bottom line is that this 14 nanosecond range is near the limit of what you could reliably measure with Scopey, and that's consistent with the theory from the M2K's bandwidth. So next, I think we need to look and see what the Siglent oscilloscope shows. One thing to keep in mind is that we did see a difference in rise time between the lowest and the highest drive strengths. So that suggests that the Raspberry Pi is really having a rise time of its signal that's at least no more than 12 nanoseconds or so. So it'll be interesting to see if the Siglent shows a smaller rise time. Maybe one more time, we'll go back to the low drive strength, reset the statistic, and see that it settles at a somewhat larger value for the rise time, which again is consistent with the lower drive strength, giving a slower rise time. The Siglent's higher bandwidth gives us more possibility of seeing signal distortion that's caused by the probes themselves. For example, the ground lead on the probe shown here, those are somewhat famous for acting as inductors, and then when you connect it to the system under test with a fast rise time, the fast rise time has high frequency energy that can incite a resonance. And then you can see this as ringing in the signal that you're trying to probe. That ringing isn't necessarily really there. In fact, it probably isn't. It's caused by the probe. So using the standard probe with its witch's hat spring clip connector and this ground lead is probably the worst way to look at this signal. But let's see what it shows before we consider some alternatives. So here's the Siglent display, and it looks great. But this is with the signal strength set to 2 milliamps, the minimum. Let's see what happens if I change it to the maximum. And now, presumably, the rise time is faster, and it's feeding quite a bit more energy into the high frequency energy into the system, and that's stimulating the ringing, probably caused by that ground lead. So this is not a good way to measure rise time, because the signal distortions here, I think, could impact that measurement. So we'll find a better way to probe. But before I leave this display, let me show you one more thing. The Siglent oscilloscope, as many do, has a bandwidth limit filter that you can put in. So I can press this button, and now there's a 20 megahertz filter in the front end of the oscilloscope. And that makes all of that distortion appear to go away. It's probably still there, but it's being filtered so you don't see it. So we probably don't want to use that to measure rise times. It would make the rise times look artificially artificially high. Don't use those filters unless you're confident that the distortions that they're hiding aren't important to you. Probably the best way to probe is to remove the ground strap and replace it with the spring clip that you see on the end of the probe. The witch's hat is also removed from the probe. And so now I have to hold the probe onto pin 8, the center onto pin 18, and then the ground spring thing next to it. Hold that carefully on a ground that's next to the pin 18. This is a little hard to do, but should result in a much cleaner signal and the possibilities of a measurement that we can trust. So the scope's set up, and I'll do the probing now. So I have to touch the ground and then the probe tip to the signal, and we can see that this looks a lot better. This is the Raspberry Pi at its maximum drive strength, and the signal looks pretty clean. And the Siglent has a statistics way of measuring rise time similar to Scopey. And if you look at the bottom above where it says type, it says rise 1 equals 3.5-ish nanoseconds. And so we're measuring a 3.5 nanosecond rise time here. And so that's a shorter rise time than Scopey was able to see even with this maximum drive strength. And this also is a number consistent with the theory. This is a 100 megahertz bandwidth oscilloscope. And so the shortest rise time that it should be able to see is around this 3.5 nanoseconds. So that suggests that with maximum drive strength, the Raspberry Pi rising edge is no more than 3.5 nanoseconds. Now I've switched the Raspberry Pi drive strength to its smallest value, 2 milliseconds, and let's see what we see. So the signal looks about the same, but now the rise time is being measured at a higher value, this time around 10 nanoseconds. So that's consistent with the smaller drive strength having a slower rise time. The number is also a little bit smaller than Scopey saw. So I think the Siglent is doing a pretty good job relative to its 100 megahertz bandwidth at measuring these rise times. And both Scopey and the Siglent, both the M2K and the Siglent are operating according to their theory. They measured rise times consistent with their bandwidths. And so obviously the 100 megahertz Siglent is doing a better job than the 25 megahertz M2K. It might make sense to end the video here. We've determined that the M2K can measure rise times of around 14 nanoseconds, consistent with its bandwidth, and the Siglent scope can measure rise times of around 3.5 nanoseconds, consistent with its bandwidth. But before I end, I'll show you another way to measure, another way to probe, and talk about its disadvantages. What we have here is a piece of coax, a 50 ohm coax, and on one end I've soldered a 1K resistor, and on the other end and next to it there's a ground lead, just the braided shield of the cable. And this probe has to be used with a 50 ohm termination on the oscilloscope. So there's also shown on the other end of the cable both its BNC connection and a 50 ohm terminator. 50 ohm through terminator. And so the problem with this method is that it loads the circuit down more. And that's a concern, especially with the Raspberry Pi set to drive at its minimum strength. By the way, this kind of cable is discussed in the third edition of The Art of Electronics by Horowitz and Hill, and they claim that this technique is how they get such clean scope output captures for their book. But it does have this issue that it loads the circuit more because there's only that 1K resistor there. And so you can't always use it. And people that know more about this than I do say in general that these cables shouldn't just be thrown together, that you have to know what you're doing to use them reliably. But it does seem, especially with a 100 megahertz scope, that you can get pretty good results just by making a cable this way, essentially thrown together with parts out of your drawer. So let's see what it looks like and whether there's any downside we can detect due to the load. So the oscilloscope is now set up with the coax probe. This probe is sometimes called a Z0 probe for some reason. And I've got the Raspberry Pi configured so that every 2 seconds it's switching between a drive strength of 4 milliamps and a drive strength of 16 milliamps. I was a little reluctant to use a 2 milliamp drive strength with this probe because of the load. It might be too much for the Raspberry Pi. And so now I'll hold the connector on here, and we see that the waveforms look pretty good. But notice that the amplitude is going up and down. The higher amplitude is the 16 milliamp drive strength, and the lower is the 4 milliamp. So the probe is loading the oscilloscope sufficiently that with a drive strength of 4 milliamps, the Raspberry Pi isn't quite able to provide enough current, for this probe to maintain full amplitude, and that's not a good thing. The rise times are being measured, and curiously, they're actually a little bit lower than what the other probe got. And there's not much difference in the rise time between 4 milliamps of drive strength and 16. I don't think I trust this measurement as much as the last one, though, just because of the load on the circuit. It's a variable that's hard to account for. The waveforms definitely look good though, so maybe Horowitz and Hill are right about it being a good way to capture waveforms for a book. Just one more thing I'll say before I end. When you're using a probe like this with that 1K resistor, the scope channel has to be set to about 20x. That's because the 1K resistor forms a voltage divider with the 50 ohm terminator, so the voltage that you sample is 1/20th. And so anyway, you have to set your scope the right way to use a probe like this, or your amplitudes will be wrong. I think the exact value to get a 20x probe is a 950 ohm resistor, but I didn't have one of those. So we'll end here. I hope you found this to be interesting and helpful.